and welcome to today's videos about stochastic gradient descent. But before we get into it, let's define gradient descent. Gradient descent is a prominent optimization strategy in machine learning and deep learning that can be utilized with the majority, if not all, the learning algorithms. Mathematically, it is a convex function whose conclusion is the partial derivative of collection of input parameters, whereas the term stochastic refers to the system that is associated with random probability. As a result, in stochastic gradient descent, a few observations are chosen at random rather than the entire dataset for each cycle. Through this course, you will learn about stochastic gradient descent, how it works, the difference between SGD and gradient descent, mini batches, and momentum in this process. So without any further delay, let's get started. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Hello everyone, my name is Shambhavi. Hope you all are doing well. So, in deep learning, and if we talk about the neural networks as well, there's a topic that's one of the most important algorithms to learn about. So, here today we are going to learn about that respective most important algorithm, that's stochastic gradient descent. Okay. So, under this stochastic gradient descent algorithm, we'll be going through several topics that are really very beneficial for you to understand in the field and in the deep learning as well as the neural networks. So, right here, we start out with the learning of the stochastic gradient descent algorithm. So, without moving to any of the topics, just quickly, I really want you to first of all go through the agenda. That what's the agenda that we are going to follow up for this respective video. So, here we have the agenda. Now, directly not jumping onto the stochastic gradient descent, here we have three terms. Let me tell you a little bit about this right here only. First one is the stochastic, right? Second is the gradient, and the third one is the descent, right? First of all, we'll be learning that what actually do you meant from gradient descent. Okay, so for that we'll be having our first topic, that's the objective of gradient descent. That what gradient descent first of all actually is and what's the objective. So for whatever the topic we are actually learning today, for that respective topic, I have described that topic in two different words. Stochastic will be the different and the gradient descent will be the different. So first of all, I'm going to talk about the gradient descent. Further, I'll be completely talking about the stochastic gradient descent. Okay, after learning about the objective and what's the gradient descent actually is, I'll be taking you towards the algorithm of the gradient descent. That what's the algorithm and how do the gradient descent actually works about. After learning about gradient descent, now we have some types of gradient descent that we'll be discussing through. And under that respective topic only, there will come one type of gradient descent, that's the stochastic gradient descent. So from there only we'll be taking up this respective topic and we'll be moving forward into our tutorial, into our video for today. So here after learning the types, we'll be dealing that what stochastic gradient descent actually is. Okay. Now, when you will learn about the stochastic gradient descent, you would find up at some places that gradient descent and stochastic gradient descent. These are somewhat same things or not, these are not same things. You would be having a little confusion into that. Yeah, because there's some common things as well into those. So for the clarification of those respective things, I'll be introducing to the topic that is stochastic gradient descent, same as gradient descent. So here under this respective one, we'll be checking about the similarities, about the differences, and then we'll be coming to the conclusion that are these same or not. Moving forward, I'll be letting you know that what's the need for the stochastic gradient descent. Then how does the respective algorithm works. Then after learning about all of these things, when we are learning about any of the respective things, so we shall be very much aware that what are the advantages of using or learning about that respective thing. Let's say what are the places, what are the advantages that why you should use about the stochastic gradient descent. So we'll be going through the advantages, and that's the very obvious thing that if something is having advantages, so there shall be some or the either disadvantages as well, and that's the reason that there are many more algorithms in the deep learning and neural networks. So we will as well be seeing about some disadvantages of the stochastic gradient descent. Now into SGD, that's the stochastic gradient descent, we have two more important terms that come. The first one is the mini batches and the second one is the momentum. So I'll be taking you through both of these, that what are these and how are these actually used about, and what do they actually mean and what are their respective uses in the stochastic gradient descent. And at last but not the least, when you'll be learning about all of these things, you would learn that we have a term that's called as convergence in the stochastic gradient descent. So we'll be learning that why does this stochastic gradient descent converge? What's the use of? Because into this respective tutorial at many places you would learn that SGD, that's my stochastic gradient descent, that converges. So why is the reason for that? Why does it do? So we'll be learning that at the last. So I hope I am very much clear that how are we going to proceed up into this respective tutorial regarding the stochastic gradient descent. All of these topics are having some real life examples as well, so that you could relate very well in the all of these respective topics. Now, one note to put up here before moving forward with any of the topic, that at some of the places, if I say SGD, so that is going to completely mean about the stochastic gradient descent. SGD is the short form and stochastic gradient descent is the full form. Okay, so please make sure that you please hear out these words and relate to whatever I am referring to here in this respective tutorial. Let's start here with the objective of gradient descent, right? So right here we have the objective of gradient descent. Okay, so that's actually, I would say that a gradient descent, it is one of an optimizing algorithm. Either you say that for machine learning or for the deep learning, it's a sort of an optimization algorithm. Now, a new term introduced by me here for you, and that's optimization algorithm. What sort of algorithms are these actually? Let me tell you in a little bit detailed way, because it would be rather than more easier for you to understand the objective of gradient descent. So, if we talk about the optimization algorithm, that's a sort of procedure, okay, in which actually what is done, it is executed iteratively. Okay, iteration means that whenever you are having some sort of range and it's completely iterating, means it's moving from one number to the other, from the other to the third number, that's a sort of iteration. So hope you're very well aware of the Python, right? So in Python we learned about the for loop. So in the for loop you must have heard about the iteration, that it is a sort of iterating thing that one after the other, whatever the condition you put out, it iterates, it goes up to that respective point and finishes up there. So the meaning of the iteration is same here as well. The meaning of the words do not change if they are referring to any of these topics here. So that's why I was talking about that optimization algorithm that's executed iteratively. And what actually happens up here, that whatever the solutions are there, it compares them iteratively, means one by one, it compares all of those solutions which are there. Okay, and after comparing of all those respective things, whatever the solution is found the most accurate, the most satisfactory. Okay, so with the help of this respective iteration and comparing of the solutions, the most accurate and the most satisfactory solution is found out. And that so is one of called my optimization or optimizing algorithm. Right? I would repeat it again. Please, I would request you to please now listen to my words very, very, very carefully, because these are the technical terms that are really very important for you to learn about, for you to understand. Optimizing algorithm is a sort of procedure in which the solutions are compared iteratively, and finally the most accurate and the most satisfactory solution is found. That respective procedure is called as optimizing algorithm. So gradient descent is a sort of optimizing algorithm of the machine learning or deep learning. Right, so hope I am first of all very much clear that in gradient descent as well, the iterations happen, the solutions are found out with the satisfactory and the accurate results. Right, so all of these things as well happens up into the gradient descent. First of all, right here I told you what gradient descent actually is. Now, what's the objective of the gradient descent? The objective of gradient descent is using iteration, it minimizes the convex function. Now, there's a convex function that's termed as fx. Okay, so the main objective of the gradient descent is that using the iterations, using different iterations, it does minimize the fx. It does minimize out the convex function. Okay, so this is what's the objective. This is what the objective of gradient descent is. This is what it actually does out. It minimizes the convex function with the help of the iterations. Okay, now rather than only minimizing up the convex function, it as well minimizes the given function or the cost function. Cost function is as well referred to the loss. Okay, you call it as a cost function, you call it as a loss, both are the same things. So it as well minimizes out the given functions or the cost functions that are your losses. So the objective of gradient descent is completely that it minimizes the convex function, it minimizes the given function, or it minimizes the cost function, or you say that as the losses. Okay, so great, hope I am clear with this particular thing regarding the objective. Let me once again put up some light once again here, then we'll be moving forward to the next of the topic. So the gradient descent is a sort of an optimizing algorithm of the machine learning or deep learning. Optimizing algorithm refers to a procedure in which the executed iteratively by comparing the results, the solutions, and finally the most accurate and the most satisfactory solution is found out. This complete procedure is the optimizing algorithm. So gradient descent is a sort of an optimizing algorithm only. The main objective of gradient descent is that it uses the iterations. Now that's what it is, a optimizing algorithm, so surely it's gonna use out the iterations. So using iterations, it minimizes the convex function that is referred to as the fx. It as well minimizes the losses and the given functions as well. So this was the complete about the objective of gradient descent. Okay, so great. Hope I am very much clear with this particular thing to you here regarding the objectives of gradient descent. Now let's learn about that what's the algorithm of the gradient descent, and right here only we will be taking a real life example for the explanation for the use of the gradient descent algorithm. Great. So here we are, the gradient descent, the algorithm. Fine. Now, before moving to any of the technical things, I would really want to give you a very quick example that what are the cases, first of all, where this respective algorithm actually helps you, where this respective algorithms helps you to do up the things. Now, I will be giving you a real life example because it's very much easier to relate out with the real life examples rather than the technical things, right? So let's get on to that. Here I had put up a picture, and that's a picture that a person is at the top of the mountain. Okay, the very top of the mountain, a hill or a mountain, whatever you say out. Now, suppose, let's say I take up example, let's say you want to climb up a very tall mountain. Okay, there's a tall mountain and you want to climb up that out as it's present up in the picture, right? Now, you have a goal set out for you that yes, I want to reach up the top of this respective hill in a fastest manner. Okay, or take it in a way that let's say you are somewhat 10 to 15 people and you have somewhat a challenge that let's say who's the person who's going to reach out the top of the mountain at the earliest. So now your respective and the foremost goal is that you have to reach out to the top of the mountain at the most fastest. Right now, you are at the bottom of that respective mountain. Now just look around. You actually did a look around you and you found out that okay, there are many ways from which you could go and reach up to that respective mountain. Right, there are many of the options which you could choose and that can take you to complete up your goal. But your way is that your main goal is to complete that in the fastest manner. It means that among those 10 to 15 people, you want to be the first person to climb up that respective mountain in the most fastest way. Now, what's the way you could do this, which respective way to choose out in that case, and how to choose that, okay, which is the respective path that is going to take you to the very first and the fastest onto that respective mountain. Now that's the place where you use the gradient descent algorithm. Right, so this actually was a sort of example, a real life example, that you have many ways for reaching on to a respective path, but what's the fastest way? That will be that the gradient descent algorithm will help you to find out that respective thing. Okay, so first of all, hope I am very much clear that what's the use and what is a sort of real life example for the gradient descent algorithm. Now, for finding out the local maximum and the local minimum of a respective given function, gradient descent is an iterative optimization algorithm. Right in the previous slide, a few minutes before, I told you about the optimization algorithm. I told you that what is an optimizing algorithm, right? So yes, gradient descent is one of our iterative optimization algorithm. What is it used for? It is used for finding out the local maximum and the local minimum of a respective given function. Now let's say the mountain is your function and you want to reach up the top of that particular mountain in the fastest manner. So with the help of the gradient descent algorithm, you would find up a path, you would find up the local maximum and the local minimum values are a range of that respective given function. Okay, hope I am clear with that. Next, that gradient descent I did already mentioned up either in the respective previous video, in the previous slide, that for minimizing the losses, that was your cost function, right? In that case, the gradient descent is used either in the deep learning or in the machine learning. The losses, whatever you figured out the losses while your function, while finding out the range, while finding out the values for your function, whatever the loss function you did get out, or whatever was the cost function. So for minimizing up those respective cases, the gradient descent is used in the deep learning or in the machine learning. Now, it as well have a exception that gradient descent is only and only used for two types of functions. Either the function is convex or the function is differentiable. Okay, other than these two cases, the gradient descent algorithm can't be used on any other type of function. So, firstly, either your function shall be a convex function or your function shall be a differentiable function. Other than these two cases, you can't use out the gradient descent algorithm onto any other type of function. Okay, so this was about the algorithm right here. Let me put up once again a little bit idea regarding these things, because yes, it's a most important one to learn here about. So for especially finding about the local maximum and the local minimum of any of the respective given functions, gradient descent is a sort of an iterative optimization algorithm that's used out. Now, I am using up this optimization algorithm many a time. So that's a sort of a procedure in which the iterations are it is a procedure in which the iteratively expected solutions come, and those expected solutions are compared up, and after the comparing of the solutions, the best and the accurate, the satisfactory respective solution is founded out. That's a sort of an optimization algorithm which is actually meant out this. So yes, gradient descent is a sort of that only. So now for minimizing the loss function, either you see that losses or you see that as a cost function. So in the deep learning or in the machine learning, the gradient descent can be used out. And it has the exception that it is only and only used onto two types of functions, the convex and the differentiables. So now, as I mentioned up in the example that you want to climb up a mountain, and now you want to do that in the fastest manner. So there are many different ways, there are many different paths, there are many different way how you could go onto the top of that mountain in the fastest one. But now you have to choose from all of those respective paths that from which I would be traveling the most fastest onto the top of the mountain. So that is the sort of place where the gradient descent algorithm is actually helps you. Now, these relate out to the terms what I referred. I referred that you have many solutions. When I talked about mountain, right? I talked about that into this respective mountain, to climb up this, you have many different ways. From that, you have to find up a one. And what I told you about the optimization, that in optimization as well, you have different solutions. You compare those solutions and find out the most accurate and the most satisfactory. That is the gradient descent, right? So now hope you are very well able to relate out the example and the gradient descent, because in the mountain as well, we have several solutions. So by comparing onto that respective solutions, that respective path for which you want to climb the mountain, you will be choosing one accurate and the satisfactory one. Same goes in the gradient descent as well. You have different iterations, different solutions, and from that you choose out one. You compare the rest and choose out one satisfactory and the accurate. That's your gradient descent algorithm. Now let's learn about the different types of gradient descents, right? After learning about the objective of gradient descent, the algorithm of gradient descent, we have that there are different types of the gradient descent as well. Let's learn about those right here. In total, we have three types of gradient descent, which are named as batch gradient descent, stochastic gradient descent, and mini batch gradient descent. Right? So these are the three types of gradient descents which we have up here. Okay? Now, talking about the batch gradient descent, what's that sort of thing actually what it is? Now, first of all, batch gradient descent is as well known as vanilla gradient descent. So, if you know about the vanilla gradient descent, then that's the same thing for the batch gradient descent as well, because that's only the second name for batch gradient descent. Okay, what it does actually, it calculates out the errors, okay, for whatever the examples you have in your training data sets. Okay, whatever the examples you have in your training data set, so it calculates out the error for all of those respective examples. Okay, but when it calculates out those errors, what's the correct time that when it does? So when all the training examples, whatever the training data sets you have taken, when all of those have been evaluated, okay, and whenever your model gets updated, after that this batch gradient descent, it is a sort, it calculates out the errors for each of the examples which are into your training data set. So this is what the batch gradient descent is. It's particularly used for calculating out the errors into your training data set, but it does so when you have evaluated all the models and when the models get updated. After that, it it calculates out the error for all of those respective data sets of the training data sets. Okay, so hope I am clear with that regarding the batch gradient descent. Fine. Now, talking about the stochastic gradient descent, so that I will be right covering on to the next slide, so I would not pay too much of attention on to the stochastic gradient descent. Okay, now moving towards the third one, that's the mini batch. So yes, we have that planned onto our agenda for today's tutorial only. So mini batch, I would once give you a very short info that mini batch is a sort of combination of the batch gradient descent and the combination of stochastic gradient descent. It's the combination of both of those respective things. Okay, so that comes under the mini batch gradient descent. So we have stochastic and mini batch, both of those covered in detail in the further slides. So I'm not going to take them right here. Okay, we'll cover that further into the respective tutorial only. I wanted to discuss about the batch gradient descent a little bit. So yes, I did told that it's as well called up first of all a vanilla gradient descent. Next, it as well calculates out the error for each example, okay, in your training data set, but it calculates when all of the models have been evaluated and when all the models get updated. After that, it calculates out the respective errors for the examples in your training data set, right? So hope I am very much clear with this respective thing to you in regards of the gradient descent, the types of gradient descent. Batch gradient descent, stochastic gradient descent, and mini batch gradient descent are the three types of gradient descents right here. So here we are with the stochastic gradient descent. Let's learn about the stochastic gradient descent in a detailed manner, and let's understand that what this respective thing actually is. So right here we are. Now, first of all, that stochastic, a different name, right? Maybe you hadn't heard that previously any time. What does that stochastic actually means? So stochastic is a sort of process that is attached with random probability. Okay, the stochastic means that it is a process which is linked or which is attached with a random probability. So that's the first of all term, that's first of all the meaning for the stochastic, that it is a sort of process which is attached or linked with random probability. Fine. So that was first of all the exams or the meaning for the stochastic. Okay. Moving forward, now let's learn about that what stochastic gradient descent actually is. So, in stochastic gradient descent, what happens that for the iterations, for each of the iterations, what do? We collect out, we select a few samples. Whatever the data you are having up, from that respective data, we simply collect out a few samples. Okay, not the whole data. Let me give you an example so that you could relate it that. Let's say here I have a picture of a library. Now, into this respective library, you have n number of books. You have n number of books, right? Now, from this n number of books, you are going to choose out some books for your reading. It's not the case that you are going to take all these books once at your home and start reading that out. Now, that's not a case, right? From this list of so many books, you are going to choose out first of all some 4 to 5 books. You would read that out, finish them, and then choose the next set of books, right? This is what same happens in stochastic gradient descent. Now, take these books as my data, and when I select up a few samples, assume that few samples are some of my books which I am going to take up from this respective library. Okay, so in stochastic gradient descent, what happens that for each of the iterations, okay, instead of your whole data, you try to pick out some few samples. You try to select up some few samples from that respective data, and this is what happens in stochastic gradient descent, right? Hope I am clear with that. Now, when the denotion of the total number of samples in a data set, whatever the total number of samples you are having up in a data set, and for that and those respective samples in a data set, you are going to use them to calculate the gradient. Okay, you're going to use them to calculate out the gradient for each iteration. That respective thing is called as a batch. Okay, so the denotion of the total number of samples in a data set which is used for calculating the gradient for each iteration is termed as a batch. Okay, so whatever the total number of samples you are having in a data set, okay, and that respective samples are used for calculating the gradient, okay, for each and every iteration, that respective samples are used for calculating the gradient. So that particular thing is termed as a batch. Okay, so great, hope I'm clear with that. So that's what is stochastic gradient descent is, that in this, for each iteration from the whole data, you pick out, you select out some few samples. Stochastic means that it's a procedure in which that is attached or linked with the random probability. Now, you are selecting a few samples, right? You're randomly selecting a few samples. It's not the case that, okay, I'm going to check out everything and then I am going to select it out, right? There are many, let's say you have many thousands, 10,000s of books. You are not going to read out the title for 10,000 and then select it out. You are going to take out randomly some, you're going to select out some randomly some books, you start reading that out. That same happens up here is as well. So that is what is termed as stochastic, that it's a process which is attached with the random probability. So whatever the few samples you are selecting from your whole data, that is what is done from the randomly, right? That is the random probability that you are doing out. This is respectively what is termed as stochastic gradient descent, right? And the batch, make sure you remember out this term that is batch, because it's really going to use up a lot in the further slides. Okay, so that's a total number of samples in a data set which are used for calculating the gradient for each iteration are known as a batch. Fine, great. So hope I am clear with stochastic gradient descent to you very well, that what this particular thing is actually, what it is used for, and how you could relate this into a real life example as well. Now, let's understand, let's compare that are these two things same or are these two things different? If same, then what are the similarities, and if different, then what are the differences? Okay, let's discuss that out in a detailed manner. Okay, so is stochastic gradient descent same as gradient descent? No, not at all. It's not same as the gradient descent and the stochastic gradient descent. Not at all same. The reason I could give you in a very detail that why I am saying that these are not the same. A very first example I did already told you when I was discussing about the gradient and the stochastic gradient, that in the gradient descent we try to take the whole data, we used to apply the iterations onto the complete data, and in stochastic gradient descent the iterations are done from in whatever the complete data you are having. From that you try to pick up few samples from that, right? So this is the main difference which is there. Now let's discuss that in detail, that what are the differences in the gradient descent and the stochastic gradient descent. Gradient descent is slow and computationally expensive algorithm. Why? Okay, 1 second. Stochastic gradient descent is fast and computationally less expensive algorithm. Slow and fast. Why? Now, reason I did already mention it up right here a few minutes before, not minutes, few seconds before only, that in gradient descent it completely works onto the whole data. In stochastic gradient descent, from the whole data, it picks up some and it picks up few samples, and onto that the work is done. So obviously if you are going to do it something for the complete, it is going to be slow, and if you're going to choose out some samples from there, then work upon that, so it's going to be fast, right? So that's the first and the very basic difference between the gradient descent and the stochastic gradient descent. Second, moving towards the gradient descent cannot be used for huge training samples. Stochastic gradient descent, it can be used for huge training samples. Reason, again the same reason, that training huge samples at one go, training a huge complete data at one go is a tedious task. But from a huge training samples, from a huge training data, picking out few samples is not a tedious task. So in that manner, Gradient descent cannot be used for huge training samples, and stochastic gradient descent can be used for huge training samples. Okay, gradient descent cannot be, and stochastic gradient descent can be. Gradient descent, the convergence is slow. In stochastic gradient descent, the convergence is much faster. What's the convergence? First of all, let's understand that in a little detail way. I would just brief you about the convergence. Listen to me very carefully. Now, whatever the iterative optimization algorithm you are applying out, here gradient descent and stochastic gradient descent, both are the optimization algorithms, right? So in that, convergence refer that it's a stable point which is actually found out at the last of the sequence. It's actually really one of the points, one of a stable point which is found out at the end of a sequence of a solution. Okay, with the help of an iterative optimization algorithm. So, with the help of an iterative optimization algorithm, whatever the stable point is found out at the end of a sequence of solution, whatever the sequence of solutions you are having, at the end of that sequence of solutions, whatever the stable point is found out, that is referred to your convergence. So that respective procedure of convergence is slow in the gradient descent and is much faster in the convergence. Okay, that's the thing. So here these were the few examples or few differences in between stochastic and the stochastic gradient descent and the gradient descent. And for after seeing up these respective differences, we can surely say that no, these things are not at all same. I would repeat it out again. In gradient descent, that's a slow and computationally expensive algorithm. Stochastic gradient descent is fast and computationally it's not an expensive algorithm, it's less expensive algorithm. Gradient descent cannot be used for huge training examples, and stochastic gradient descent can be used out for the huge training samples. In gradient descent, the convergence is slow, and in the stochastic gradient descent, the convergence is much faster. So convergence, actually I did already mention up that when at the end of a sequence of a solution you found out a stable point, there's a stable point at the end of a sequence of a solution through an iterative optimization algorithm, that's referred to my term that's called as convergence. Okay, so great. Hope I am very much clear that what are the differences between the gradient descent and between the stochastic gradient descent, and why are these not similar to each other. Now we'll be learning about that why stochastic gradient descent is needed. What's the need of this respective thing? Right, let me take you forward here. Now, there are three reasons which I had mentioned up here for the use of the stochastic gradient descent. Okay, the very first one is that stochastic gradient descent does the calculations much faster than gradient descent. Now, whatever the calculations you are having up here in the stochastic gradient descent, that are done very much faster than the gradient descent. Now, whenever we are using up any algorithm, what we want? We want that respective algorithm shall perform our work faster, right? That's the reason why we use up the algorithms. Now, into that respective case, whatever the algorithm will be performing the work faster, that surely will be used out. So, stochastic gradient descent, it performs the calculations much faster than the gradient descent. So, this is the very first reason that why stochastic gradient descent is needed. Moving towards the second one, that other than the stochastic gradient descent algorithm, there is none of the other algorithms which can give you the better results on the expected losses. You call that as losses or you call that as a cost function. Both are absolutely the same thing. So other than stochastic gradient descent algorithm, there is none of the algorithms which can give you better results on the expected losses. Right. So for getting the better result onto the expected losses as well, stochastic gradient descent is the algorithm which is used out, which is actually used. Fine. Then now stochastic gradient descent updates performs the updates very frequently, and because of that it converges onto the data set very easily. So SGD, that's my algorithm, that's my stochastic gradient descent algorithm. It performs up the updates very frequently. Okay, whatever the updates are there, it performs those very frequently, and because of very frequently performing of the updates, it converges onto the data sets very easily. Convergence, I did already told up that after the iterations are done and after the sequence, all of those sequence of solutions are there, so those are there is found out a stable point, right? So that respective stable point is referred to as the convergence. But this thing happens in the iterative algorithms only, right? So yes, stochastic gradient descent is an iterative algorithm, right? So in that case, it converges onto the data sets very easily. This difference we did as well see out into the previous slide, where I was telling you that what are the differences, that why we say that gradient descent and stochastic gradient descent are not similar to each other. Right there as well I mentioned up this particular point. So now if you think actually whatever the algorithm you are using, it is converging very easily, it is doing the calculations in a faster manner, for the losses it is giving you the better results. So surely that respective algorithm is needed, right? Surely that respective algorithm would be needed, and that all are the reasons that why the stochastic gradient descent is needed and is as well used out, right? Let me take you to this once again because it's one of the most important topic into that respective tutorial which I am discussing right here. So the calculations which are done up here in the stochastic gradient descent are very much faster than the gradient descent. And other than the stochastic gradient descent algorithms, there is no such algorithm like that which could give you the better results on to the expected losses, or you see that as cost function. So it is one of the algorithms which really gives you the good results, the better results on the expected cost function or the losses. And the convergence of the data sets is done very easily using the stochastic gradient descent algorithm. So these are the reasons that why we use and why this SGD is needed out, right? So hope I am clear with this particular thing to you, that what are the reasons. Okay, now let's learn about that. How does this stochastic gradient descent algorithm works about? We heard about the uses. We till now we learned that what is it, why it is used out. Now let's learn about that how this respective algorithm works out. So here we are, right? Next for this respective thing. Now, How does the stochastic gradient descent algorithm works? We very well know that stochastic gradient descent is an iterative algorithm. Right, that we are learning from the very starting of this tutorial. I have repeated not less than 20 times in this respective tutorial that stochastic gradient descent and the gradient descent, these are termed as the iterative algorithms. So the stochastic gradient descent, it starts on a function with a random point. Stochastic means that only, right? Random probability. A procedure, a process for dealing with a random probability, right? In this, actually, what you do, you take up some random points, right? That what is done. So firstly it starts on a function with a random point, and in steps it travels down the slope until the time it reaches the function's lowest point. So till the point the function's lowest point is not reached, it travels down the slope. Okay, it travels down the slope until the time the function's lowest point is not at all reached. So it starts on a function. Okay, it firstly starts on a function with a random point, and in steps it travels down the slope. Okay, in steps it travels down the slope until the time it reaches the function's lowest point. Now here is an example which is given, and here you have a path, right? You have gone onto the top of the mountain. Now only going to the top of the mountain was a task. That's completely, let's say, filled up. Now you want to come back to that as well, right? So you have to reach out the lowest point of this respective mountain, right? That same happens up in the gradient descent as well, that it starts on a function with a random point, whatever the random point has been chosen or taken, it starts on that with a function, and it travels down to the slope until the time it reaches the function's lowest time. Till the time the lowest point, the minimum point of the function is not reached, it travels and travels and travels down the slope. This is how the stochastic gradient descent algorithm works. You reached onto the top of the mountain. Now traveling back is as well one of the work which you need to do, right? So that's the thing where this stochastic gradient descent algorithm works about. Okay. While equating the slope of the function to zero, where the optimal points cannot be found, stochastic gradient descent is the algorithm which comes in use. Now, when you are equating the slope of the function to zero, it means when you had put up the equation, and in that equation, the slope of the function is actually zero, and you are not able to find out any of the optimal points on that respective case. So this stochastic gradient descent is the algorithm which helps you to do that out, which comes in the use. So when you did out the equation, you equated that out, you found out the things, and the slope of the function comes to zero. When the slope of the function comes to zero, now you are not able to find out the optimal points onto that, right? That's the case. That's the place where stochastic gradient descent comes in the use. Okay. So this is how this respective algorithm works about that. It works in our iterative algorithm that we know. So it starts with a function with a random point. It travels down the slope until that respective point, until that respective time it reaches the function's lowest point. Till the time it is not going to reach out the function's lowest point, it is going to travel down the slope. It is going to travel down the slope. So whatever the function you are having, and into that respective function, whatever is your lowest point, till the time it doesn't reaches out, it is going to travel down to the slope. Okay. So this is how the stochastic gradient descent algorithm works about. This is how it actually works about, right? So hope I am clear with this particular thing to you, that how the algorithm works and what are the things which you have to make sure here and what it is used for. Now let's learn about the advantages of the gradient descent. Let's learn those about. Okay. So, we are going to learn about the advantages of the stochastic gradient descent. Okay, we are going to see that out. Now, what are the advantages of the stochastic gradient descent? We did already mention out some into the previous slides, in the previous deck, which we had seen. But right here, I have the things up into the detail. The very first advantage of stochastic gradient descent is that it is easier to fit in the memory. Okay, so it's very easier to fit up in the memory. Fine. So if a thing is absolutely easy to fit up in the memory, so yeah, that is one of the good advantages of stochastic gradient descent. Next, only one sample is processed at a time, so it's computationally fast. We did learn about that. Yes, it is a computationally fast, right? It actually works computationally faster rather than the gradient descent, right? So the reason for that is that at one time, okay, at a time, only and only one sample gets processed. So if anything is getting processed one by one, so yes, obviously that respective thing is gonna be computationally fast, and that's the goes in the stochastic gradient descent, that the samples which you are having up here, that respective sample at a time, only one sample gets processed. So it is said that stochastic gradient descent is computationally fast. It can work faster on larger data sets as it updates the parameter quickly. We learned about that stochastic gradient descent works very faster onto the larger data sets, right? Whatever the large data sets you are having, stochastic gradient descent works very faster. Now reason is that whatever the parameters are there, it updates those parameters very quickly. Now, when the updation of the parameters is fast, so obviously that stochastic gradient descent is going to work faster on to the larger data sets. Okay, so this is the thing, this is the reason, this is the place where we could say that the parameters get updated quickly, and because of that it can work faster on the larger data sets. Okay, next, it has frequent updates, and because of that it helps to get out of local minimums. So there are very frequent updates, right? We did already see this out into the previous thing, that it really have up a frequent updates, right? So because of those frequent updates, it helps to get out of the local minimums. Okay, whatever the local minimums are there, it helps to get out of those local minimums. Fine. So whatever the local minimums are there, it helps to get out of those local minimums very quickly, right? So this is one another advantage of the stochastic gradient descent. So first of all, it's easier to fit up into the memory. Second, it is computationally fast. Reason for that is that at one time, only one of the sample is processed. It updates up the parameters quickly. So because of that, it can work up on the larger data sets in a faster manner. And it adds frequent updates. So because of having up the frequent updates, it helps to get out of the local minimums. Right? So hope I am clear with the advantages of the stochastic gradient descent. Now let's have a look at what are the disadvantages of the stochastic gradient descent, right? Let's quickly have a look into that. Taking you forward right here. So here I have mentioned the 4 disadvantages of the stochastic gradient descent. Okay, the very first one goes that the steps taken towards the minima are very noisy. Okay, we saw actually that in stochastic gradient descent, what happens that it has the slope and it reaches up to the lowest point, whatever is the lowest point of the function. So it steps in the slope and reaches up that respective lowest point. Right, this is what was happening up in the stochastic gradient descent. Now the steps which are taken towards the minima are very noisy. So for traveling to the minima, for finding up the local maximum and the local minimum, that's the local maxima and the local minima, the steps which are taken up in the stochastic gradient descent are very noisy. Now noisy doesn't mean that they sound, but it actually means that it's a sort of a little bit messy or some things like that. Okay, so this is the idea, the very first disadvantage, that yes, it travels up to the local maxima and minima. That is so very true. But whatever the steps are taken up here for traveling towards the minima, so those respective steps are very noisy. Okay. Next goes that it might take longer to achieve convergence because of noisy steps. Now, the convergence we did already see about the convergence. I have told about that many a times in this particular, so I'm not going to repeat that out. So it could be the thing that it might take longer to achieve convergence because of the noisy steps. So whatever the noisy steps are there which are taken towards the minima, so because of those respective noisy steps, the convergence, which was one factor which was achieved out by the stochastic gradient descent, might take some longer time. Okay, so it takes up some longer time to achieve up the convergence. And that's so because of the noisy steps which are taken towards the minima. The steps which are taken towards the minima, that are so very noisy, right? And because of those respective noisy steps only, it might take longer to achieve out the convergence, right? So hope I'm clear. Moving next, frequent updates are very expensive. Now we just saw that the stochastic gradient descent has frequent updates, right? Frequent updates are there in the stochastic gradient descent. That was one of the advantage. Now into that case, it was at one place it was benefiting us with some advantage, right? It was benefiting us with some good thing. Now that so is very true, but the updates which are very frequent, that are too expensive. So whatever the frequent updates are there, those respectives are very expensive. Okay, so that's one of the other disadvantage of the stochastic gradient descent. And dealing with only one example at a time, it loses the advantage of vectorized operations. Now in stochastic gradient descent, what it does, it actually deals with only one example at a time. Right, we just saw few minutes before in this that there are some examples, and through that when we saw about the algorithm of the stochastic gradient descent, right? So whatever the examples are there, so at one time it only deals with the one example, right? So due to that, where the loss is there, what we are actually losing, so it losses of the advantage of the vectorized operations. Okay, so whatever the vectorized operations, whatever the vectors you could apply up here, so it losses of the advantage of those respective operations. And what losses of this, so dealing with only one example at a time, losses of this irrespective example of the vectorized operations. Okay, so these were the few disadvantages of the stochastic gradient descent which we have up here. So the steps which are taken towards the minima, those are very noisy. It could take up a longer time to achieve the convergence. It achieves the convergence, that is so true, but it might take up a longer time. The reason for that is the noisy steps which are caused by the steps which are taken towards the minima. Right, now we have frequent updates in the stochastic gradient descent, very true, but whatever the frequent updates are there, those perspectives are very expensive. Okay, and it loses up the advantage of the vectorized operations. Why and how? So at one time it only deals with one example, right? So because of that, it completely losses up the advantage of the vectorized operations. Okay, so great. Hope I'm very much clear with the disadvantages of the stochastic gradient descent as well. That what are the disadvantages which you have up here. Now let's learn about the mini batches in the gradient descent. So what are these mini batches which we have in the gradient descent? Let's learn about them in a little bit of detail. Now, what happens up here for the mini batches actually? So whenever you want to calculate the model error, right, we whatever the model error you are having, whenever you want to calculate that out, and whatever the model coefficients you are having, you want to update those respective model coefficients. Now let's say you are training up a model and you have the model. Now into that, whatever the model error is there, you want to calculate that out. Okay, and what are the model coefficients you have taken, you just want to update those model coefficients. Now, for doing up this, there's a variation of the gradient descent algorithm, okay, for calculating the model error, and for the updation of the model coefficients, there is a variation of the gradient descent algorithm, okay. And what it does, what variation of the gradient descent algorithm? So what the variation of the gradient descent algorithm which takes place, it helps us in the splitting of the training data sets into small pieces. Whatever the training data set you did have and whatever the training data set you are working upon, it helps you to split out. Split means that like simply split out means that like separating the ones, okay, separating the data sets into small pieces. Splitting means separating, you could say, okay. So whatever the training data set you are having, the variation of the gradient descent algorithm helps you to split out that respective training data set into very small pieces, okay, and that so is called as the mini batches. So for calculating the model error and for updating the model coefficients, so there's a sort of variation of the gradient descent algorithm which helps you into the splitting of the training data set into small pieces, and that respective thing is only known as mini batches, okay. So this is what first of all mini batches is, that actually there's a variation of the gradient descent algorithm, okay, for the splitting of the training data sets into small pieces. So with whatever the training data set you did have and whatever training data set you are actually working upon, so there's a variation of the gradient descent, okay, a variation, a change is there in the gradient descent algorithm, and that respective change helps you in the separation of that training data set, in the separation, in the splitting of that respective data set into small pieces. Let's say you are having a very big data, okay. Now from that respective data set, you pick out some small pieces of that respective data set, okay. So that respective thing is known as mini batches. Great. Now this mini batches, the term which I told you right here, so it's one of the most common implementation of the gradient descent, okay, and that so is founded in the deep learning. So in the deep learning, it is one of the very common implementation, means that at mostly of the cases this respective mini batch is used out, okay, and it's a common implementation of the gradient descent. Now how could I say this out? So just like take your mind a few minutes before, there I told you that there were three types of gradient descents. I told you, right, that first one was the batch, second one was the stochastic, and third one was the mini batch, right? You remember it out. So that's what something is right here, that is the mini batches in gradient descent. Okay, so this is the one only which we were just talking about. So it's one of the, yeah, I just mentioned it out that it is one of the very common implementation of the gradient descent, and that so is founded up in the deep learning. Okay, Next is that for the learning algorithm, whatever the learning algorithm we are having up here, uh, whatever the learning algorithm, it requires up a configuration of an addition which is mini batch size parameter. So for the learning algorithm, it as well requires up some special features. It as well requires up some special configuration. So that respective special configuration is known as mini batch size hyperparameter. Okay, so yeah, that's a sort of parameter only, but that's a sort of little different thing. But it is used in the case for the learning algorithm. For wherever you are using this mini batch in the learning algorithm, so there it requires of the configuration and an addition which is mini batch size parameter. Right, so hope I'm clear with that. So for calculating of the model error and the updation of the model coefficients, uh, in the gradient descent algorithm, there's a variation. There's a changement which helps in the splitting of the training data sets into small pieces. And this respective thing is called as mini batches. Now, in the gradient descent, it is one of the most common implementation. Okay, in the gradient descent, mini batches is the most common implementation which is in particularly used and founded up in the deep learning. And for the learning algorithms, this mini batch requires up a special configuration, a special addition which has to be used up, and that respective thing is known as mini batch size hyperparameter. Right? So great. Hope I'm very much clear with this mini batches in the gradient descent as well. That what are the mini batches which we have up in the gradient descent? What are these used about? And where is this respective thing taking place? And what are these actually? So let's talk about the momentum in the gradient descent. That what's this term momentum in the gradient descent, and what is it actually used about? So right here we are on to the momentum in gradient descent. Now, for calculating the exponential weighted average of the gradients, okay, whenever we want to calculate up the weighted average, that is in the exponential form, exponential weighted average of the gradients, whatever the gradients are there, whenever you want to calculate up the exponential weighted average of that, and after that you have to use up that same gradient for updating the weights. Okay, listen to me once again very much carefully. There is a gradient which is used for the calculating of the exponential weighted average, and after that the same gradient which was used for the calculation, that same gradient is used out for the updating the weights. This respective thing is called as gradient descent with momentum. The same gradient which is used for calculating the exponential weighted average, and the same gradient that's used for updating the weights, that is known as gradient descent with momentum. Okay, listen to me once again very carefully, because yes, that's an important term which you have up here, momentum. Okay, now let's say you have up a gradient, okay, and now from that respective gradient, firstly what you do, you calculate about an exponential weighted average. Okay, whatever the weight was there, you calculate the average for that, and you make that in the exponential form. First of all, you do this out. Okay, then the gradient for which you calculated that weighted average, for that respective same gradient, you update the weights, whatever the weights are there, you update that out. So this is called as gradient descent with momentum. When doing a both of these respective things with one single gradient in that respective term, that respective procedure is known as gradient descent with momentum. Okay, so hope I'm clear with that. Now, whatever the functions you have up in the gradient descent in momentum, okay, whatever the functions you are having up in the gradient descent in momentum, those respective functions are faster than the regular algorithm of the gradient descent. We have one, first of all, we just learned about one algorithm that was gradient descent. Right, so whatever the functions you are having in that normal gradient descent algorithm and whatever the functions you are having up in the gradient descent in momentum. So the functions in the gradient, the functions which are for the gradient descent in momentum that are faster than the normal gradient descent algorithm. Okay, so in this respective one, that's the gradient descent in momentum, the functions are faster than the normal gradient descent algorithm which we studied few minutes before. Okay, so why the reason could be, see, the reason could be that there are from the one gradient, when you are able to do out some two different sort of things and you could use the same gradient, so obviously the functions which are there in the gradient descent in momentum, they would be faster, right? And that's what you are able to do up here from that respective gradient descent with momentum. There you are able to calculate out the exponential weighted average, okay, of the gradient, and for that same gradient you are going to use for the updation of the weights. So in that case, the functions which you have up in the gradient descent and momentum are are faster rather than the normal gradient descent algorithm which we have about. Right? So great. Hope I'm clear with the momentum in the gradient descent as well. That what does this respective momentum in gradient descent means, and in comparison of the gradient descent in momentum and the gradient descent regular algorithm, which of the one is faster and the functions in which of the one is the faster. Right? Hope you have a very clear idea with this particular thing. Let's learn about this respective topic, that why does stochastic gradient descent converge? Now, firstly, how it has been analyzed that there is a convergence in the stochastic gradient descent. So there were some theories, and with the help of those respective theories, it was analyzed that there is a convergence in the stochastic gradient descent. Okay, like through that it was analyzed the convergence of the stochastic gradient descent. Now, uh, whatever the learning rate is there, okay, whatever the learning rate is there into a model, whenever there is a decrease into that respective learning rate, okay, whatever the appropriate rate, whatever the normal rate was there, so whenever there is a decrease in the learning rate with that appropriate rate, so what is found out, there is a very little assumptions. Okay, whenever there is a learning rate decrease in the learning rate, there are very little assumptions which can be which can be made out. So there are very less assumptions which can be made out whenever there is a decrease in the learning rate. Okay, then if this thing is happening, then the convergence of the stochastic gradient descent is surely to a minimum. It means that whenever there is a decrease in the learning rate with an appropriate rate, and now there will be very less assumptions which are subjected, then in that respective case, there is a convergence up to the minimum into the stochastic gradient descent. The convergence is minimum into this, okay? And this happens whenever the objective function is convex, okay, whenever the objective function is convex. So this respective thing is happens. And if whatever is written right above, like if there is no decrease in the learning rate, there is no mild assumptions, there is no minimum convergence, if all of these things do not happen, then it converges to the local minimum. There are two terms, global minimum and local minimum. So whenever there is decrease in the learning rate, then the convergence of the stochastic gradient descent is to the global minimum. And whenever there is no decrease in the learning rate, then there is the convergence to the local minimum, right? Two different terms that are to be very much taken care of with the two different terminologies. Whenever the decrease is found up in the learning rate with an appropriate rate, whatever the appropriate rate was there, and if there is a decrease in the learning rate, so then there will be very mild assumptions which are subjected. In this particular case, a global minimum, a convergence of the global minimum in stochastic gradient descent takes place. And whenever the objective function is convex, whenever the objective function is convex and the decrease is in the learning rate with the appropriate rate, then there is a convergence that up to the global minimum of the stochastic gradient descent. And whenever there is no decrease in the learning rate and all of the things which were written right above, those are not, that respective thing doesn't happens out, whatever was written, if the same doesn't happens, then in that case it converges up to the local minimum. So local minimum and global minimum, two things are there that are really way to be taken care of. That one, it converges to the local minimum when it converges to the global minimum. So when there is decrease in learning rate, it converges to the global minimum, and whenever there is no decrease in the learning rate, it converges to the local minimum. Right? So hope I'm clear with this respective thing to you, that why does this stochastic gradient descent converges. So we could say that the convergence of the stochastic gradient descent depends upon the learning rate, right? Howsoever there is a increase or decrease in the learning rate, according to that only the convergence is taken place up to the local minimum or global minimum, whatever the sort of learning rate is there, then it actually depends upon. So if there is a decrease in the learning rate, so it converges up to the global minimum, and if there is an increase in the learning rate, so it converges up to the local minimum. So this is what is actually happening about. This is what actually takes place up here for the convergence of the stochastic gradient descent. So these things were actually analyzed, that there is a convergence in the stochastic gradient descent. So these respective things were analyzed with the help of some theories, and after that analyzation, this respective thing was found out that a decrease in learning rate with an appropriate rate leads to the convergence of stochastic gradient descent to the global minimum, and the increase in the learning rate with an appropriate rate leads to the convergence of the stochastic gradient descent to the local minimum. Right? So hope I'm clear with this respective thing to you too, that how does the stochastic gradient descent converges, right? Hope I'm very much clear. Now let's take the summary of all the respective topics which we did study up till now. Okay, so let me take you back to the very first slide right here from where we did started up this respective thing, and let's take up a summary and let's see that what were the topics which we discussed up till this respective place, right? So we started up from the objective of the gradient descent. We learned about the gradient descent, that it is one of the optimizing algorithm of the machine learning or of the deep learning. Okay, and that's a respective optimizing algorithm of machine learning or deep learning is known as the gradient descent. Okay, this is what actually happens up here. Now, what is the real objective of the gradient descent? So the objective of the gradient descent is that with the help of the iterations, with the use of the iterations, what it does, it minimizes up the objective convex function that is termed as fx. So with the help of this using the iterations, it minimizes that respective out. Okay, it as well minimizes the given function or the cost function. So whatever the given function is there or whatever the cost function is there, it minimizes up those as well. So this was the respective objective of the gradient descent which we did saw. Next, we saw about the gradient descent, the algorithm, that how does this actually works about. So here we just saw up an example that let's say you want to reach up to the top of the mountain. Okay, you have some of the friends with you and you all are gonna climb up the mountain. You want to reach up to the fastest to the mountain. Now you saw around you, and there are many respective ways, many respective paths from which you could reach up to the mountain, but from there you want to choose up the very easiest sorry, you want to choose up the fastest path, that from which is the fastest path from which you could reach up or climb up to that respective mountain. So this is the place where the gradient descent algorithm comes and helps you out. So always for finding up the local maximum and the local minimum of a given function, the gradient descent algorithm is used. So gradient descent is an iterative optimization algorithm, right? So for that respective optimization algorithm is used out for finding up the local maximum and for finding up the local minimum. Now, whenever you want to reduce, whenever you want to minimize the loss function or the cost function, so in that respective case, gradient descent is used in the deep learning or in the machine learning. Okay, so for minimizing the loss function or the cost function, gradient descent is used in deep learning or in the machine learning. Now, gradient descent algorithm can only be used in the two types of functions. So those are either in the convex or the differentiable functions. Other than these two types of functions, gradient descent doesn't work upon any of the third kind of function. Okay. Then we saw about the types of the gradient descent. So in detail, we saw about three types, that were batch gradient descent, stochastic gradient descent, and the mini batch gradient descent. We after that saw about the stochastic gradient descent. So what was that? First of all, we learned about that what stochastic means. So that's completely a process which is attached or linked with random probability. So stochastic means it's a process that is attached, or you could call that as linked with the random probability. Now here we took an again example that there was a library, and into that there were about thousands, 10,000s of books. Now you want to go there and read and pick up some books for you. So it's not that case that once in a go you are going to take out that 10,000 books, right? You're going to take out some respective books from there, some 4, 5 or 10 books from there. You're going to read them, finish them out, then you're going to take out the next pair of books. This is how you do. Same happens if in the stochastic gradient descent. So whatever the whole data there is, whatever the data is there, the complete data, from that respective complete data, a few of the samples are only selected. Okay. So the denotion of the total number of samples in a data set which is used for calculating the gradient for the each iteration is termed as a batch. What is this batch is actually? So whatever the total number of samples are there in a data set, okay, the samples which are there in a data set and which are used for calculating the gradient for each iteration. So that respective thing is known as a batch, right? Then we saw about that is stochastic gradient descent same as the gradient descent. So we differentiated between those and we found it out that no, these are not the same. So what was the differences? The differences were that the gradient descent is slow and computationally expensive algorithm, rather than stochastic gradient descent is fast and computationally less expensive algorithm. In gradient descent, it cannot be used for huge training examples, rather than stochastic gradient descent can be used for huge training examples. Gradient descent, the convergence is slow. Rather in stochastic gradient descent, the convergence is much faster. So these were the few differences which we saw between the gradient descent and between the stochastic gradient descent. And from there only, we just said that, okay, these are not the same. Next, that why is this stochastic gradient descent needed? What is the use of that? Now, we have the three reasons mentioned up here for the use of the stochastic gradient descent. First one, that stochastic gradient descent, it does have the calculations very much faster than the gradient descent. So rather than the gradient descent, the calculations happens up very much faster in the stochastic gradient descent. Okay. Next, other than the stochastic gradient descent algorithm, there is none of the other algorithm which gives you the better results on the expected losses. So whatever are the expected losses, for getting up the best results onto those respective expected losses, the stochastic gradient descent is the algorithm which can surely be used about. Okay. Now, the stochastic gradient descent, it performs up the updates very frequently, and because of that, it converges on the datasets very easily. So, the frequent updates are performed in the stochastic gradient descent, and because of that perspective only, it simply converges the datasets in a very easy manner. Okay. Now, how does this stochastic gradient descent algorithm work? So, how does this respective algorithm works about? Now, we know this thing very well that the stochastic gradient descent is an iterative algorithm. We know this out very well that it is an iterative algorithm. So, what it does, it firstly starts with a random point on a function. Okay, it firstly starts with a random point on a function, and it travels the steps down the slope until that respective time it reaches the function's lowest point. So up till the time it doesn't reaches out the function's lowest point, it travels down the slope. Okay, and this stochastic gradient descent, it is a very well-known iterative algorithm. So at the very first, it starts on a function with a random point, and in steps it travels down the slope until the time it reaches the function's lowest point. Okay, this is what happens. Now, while equating the slope of the function to zero, where the optimal points cannot be found, stochastic gradient descent is the algorithm which comes in use. Now, whenever you are equating up the slope of the function to the zero, and the optimal points which are there which that are not able to be founded out, so in that case the stochastic gradient descent is the algorithm that comes in the use. Then we saw about the advantages, that what are the advantages of gradient descent. So yes, it's easier to fit up in the memory. At one time only one sample is processed, so computationally fast. It can work faster on the larger data sets because it updates the parameter quickly, and it has frequent updates, and because of those it helps to get out of the local minimums. Now, after having some of the advantages, the stochastic gradient descent algorithm was having some of the disadvantages as well. So let's have a look upon those. So whatever the steps are taken towards the minima, those respective steps are very noisy. So to achieve up the convergence, it might take up some longer time because of the noisy steps which are taken towards the minima. Now, frequent updates are there, but those are very much expensive. And dealing with only one example at the time, it loses up the advantage of the vectorized operations. So these were some disadvantages of the stochastic gradient descent which we saw. Then we used and saw about the mini batches in the gradient descent. So what are these mini batches? So whenever you want to calculate the model error or update the model coefficients, so there's a variation of the gradient descent algorithm. Okay, that helps you in the splitting of the training data set into small pieces, and this is called as mini batches. Now, it is one of the most common implementation of the gradient descent that's founded up in the deep learning. And even for the learning algorithm, what it does, it requires a configuration of an addition, and that is mini batch size hyperparameter. So for the learning algorithm, it requires a configuration of an addition, and that so is the mini batch size hyperparameter. Fine. Then we saw about the momentum in the gradient descent. So there is a gradient, and from the same gradient, when you calculate out the exponential weighted average, and when you calculate out the and with the same gradient when you update the weights, so that respective one is called as gradient descent with momentum. So whatever the functions are there for the gradient descent and momentum, Those are faster than the regular algorithm of the gradient descent. Those respective functions are faster. Moving further, we saw that why does the stochastic gradient descent converge? Because from a very long time in the complete tutorial, we were seeing that it converges, but why does it converge? So the convergence of the stochastic gradient descent has been analyzed using some of the theories. So whenever we saw a decrease in the learning rate with an appropriate rate, so there are some mild assumptions which are subjected. Then in that case, the convergence of the stochastic gradient descent is global minimum. And if there is an increase in the learning rate with an appropriate rate, then the convergence of the stochastic gradient descent is the local minimum. So when it is the global minimum and when it is local minimum, that I did mention up, and it converges on the dependency of the learning rate. So the stochastic gradient descent converges up onto the because of actually the learning rate with an appropriate rate, right? So hope you are very much clear with this stochastic gradient descent. Hope you are very much clear with this particular thing, that what is the stochastic gradient descent, what is the gradient descent, what are the advantages, disadvantages, real life example, the algorithms, the working, the mini batches, the types of gradient descents, the momentum, and why does this actually converges about. Right, so hope you are very much clear with all of those things, and we hope you enjoyed up this respective tutorial. So here we have came up an end to this respective tutorial. So thank you so much for watching this out. So this is all for this tutorial. Till then, thank you and take care.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.